After discussing about the continuity, differentiability and differentiation, having a discussion about the roles and Lagrange's mean valued theorem, I want to tell you what are the applications of derivatives. In fact, the application of derivative, we firstly begun with its subtopic that is known as rate of change of quantities. In general, with simplest example, if I introduce you what is meaning by the rate of change, if any train is moving, any car is driven by the driver, any person is on the walk, what we find that our position remain to change with respect to what? It is with respect to time. So, change of one variable with respect to other, it is known as the rate of change of quantities, and definitely to solve the problems of this subtopic comes under the application of derivatives. When we talk about the application of derivatives and we opt for such a topic, what happens? It will be very clear to you if I discuss a question where find the rate of change of the area of a circle with respect to its radius when the value of radius is 5 centimeter. Question is very simple. What we want to find? We want to find the rate of change in the area of a circle when the radius of the circle is 5 centimeter. If I take an example, suppose you have thrown a piece of stone in a quiet lake, then what we observe that water start moving from that particular point where this stone hits, and we find the increasing circles. So, there may be some more questions. If we are throwing a stone in the quiet lake in a pond, then we find that the circles are concentric circles are formed. So, their radius increases, their surface area increases, their circumference increases every moment. So, this kind of change comes in the topic rate of change. And in general, if a question find the rate of change of the area of the circle, if the radius is r, we know that the area of the circle is given by pi r square. On differentiating both sides with respect to r, what we can say, dA upon dr is equals to 2 pi r is equals to what? 2 pi r. But they are asking the rate of change in area at particular time when the radius is 5 centimeter. So, to calculate it, we can say dA upon dr is equals to 2 pi r means what? 5. The value of rate of change in area at the moment when radius is 5 is equals to 10 pi centimeter square. So, ultimately, as and when any question comes when one variable is increasing or decreasing and we need to calculate the change in the second variable which is related to the first one, then this type of problems, these type of queries deal with the topic rate of change of the quantities under the chapter application of derivatives, as I discussed a problem here. Now, I am taking another example where the proper use of the derivative of the change rate will be applied. Question is an as of a variable cube. Cube, we are very much familiar. A cuboid whose all edges are equal is known as the cube. As of the variable cube is increasing at the rate of 3 centimeter per second. Any cube which is variable is damped, heated, or any physical change is made in such a way that its edge side is increasing every second 3 centimeter. Let us suppose if I talk about the solution, because they are saying that edge is changing at the rate of 3 centimeter per second find the rate of change in its volume and surface area at the instant, at the condition when the length of the edge is 10 centimeter. Anyway, I can assume let the edge of the cube is the variable, that is x centimeter. So, we are given dx upon dt because here 3 centimeter per second. Change in the edge at particular time is 3 centimeter per second. So, dx upon dt is 3 centimeter per second given. They are asking what is the rate of change per second in its volume and the surface area. So, for volume, we know that volume is given by x cube. Volume is given by x cube. On differentiating this both sides with respect to time, because dx upon dt is given and the rate of change in the volume is required per second. So, on differentiating this, we can implies dv upon dt is equals to this become 3x square dx upon dt. So, now the rate of change in the volume with respect to time is coming out to be dv upon dt is equals to 3x square dx upon dt. We can put the value of x 10 and the value of dx upon dt as 3. So, the answer, that is the rate of change in its volume, is 3 into 10 and in place of dx upon dt 3. This become 900 centimeter cubic per second. They are also asking what is the rate of change in its surface area. We know that the surface area of the cube is given by 6x square. If this part is differentiated both sides with respect to t, then the left hand side will convert to ds upon dt is equals to 12x dx upon dt. If these two values, that is x at instant 10 and the dx upon dt 3, if these two values are put, this answer will be 360 centimeter square per second. So, the problems where rate of change is given with respect to time or with respect to edge, we have to think and accordingly we have to apply. As I explained you how to obtain the rate of change in volume and surface area if the rate of change in the edge of the cube is given. Now, I am taking one more example where one variable or other will require that how to apply. A ladder 5 meter long is leaning against the wall. If I explain you it with the help of figure, suppose this is a wall and this is the ground. This is the ladder 5 meter long. A 5 meter long ladder is AB. Its foot is A and top is B at wall. Say for example, this part is x units, x meter and height is y. Question says, a ladder 5 meter long is leaning against a wall. The bottom of ladder, this part is pulled along the ground, then what will change and what will not? Remember, ladder may be pulled even to any position. Its length will not change. It will remain 5 meter. What will change? The distance of the foot of the ladder from the foot of the wall. This x may increase or decrease as per pulling, and the height of that part of the wall where the top of the ladder is touching, these two will change, but this will not change at all. A ladder 5 meter long is leaning against a wall. The foot of the ladder is pulled along the ground from the wall at the rate of 2 centimeter per second. dx upon dt is given to us 2 centimeter per second. Find the rate of change in the decrease of the height. They are asking if the foot of the ladder is pulled in such a way that every second its height is increasing 2 centimeter, then the top of the ladder will come down, then in the height there will be a decrease. That rate of change of the decrease is required when they have given the value of x, that is the foot of the ladder from the foot of the wall is 4 centimeter. As per the application of the Pythagoras theorem, we can say x square plus y square is 25. Base square plus perpendicular square is equals to hypotenuse square. Here in place of x, if I put 4, this will be 16 plus y square is 25. So, with this part implies the value of y will be 3 centimeter. So, obviously, when this part is 4, then height has to be 3 to keep the length of ladder as 5 meter. It is overall meter, so I will take it in the meter. This part is also in the meters and this part is also in the meters. Rate of change is also given, that is it is changing 2 meter per second. So, we have to take it every unit in the meter. Now, what is happened? Y is come out this, and if I take again x square plus y square is equals to what? 25. X square plus y square is 25. On differentiating both sides with respect to t, what we will find? This will be 2x dx upon dt plus 2y dy upon dt is equals to what? 0, because constant differentiation is 0. This 2 will be taken common, we will get x into dx upon dt plus y into dy upon dt is equals to 0. Answer of x is given 4. So, we will say it is 4. Dx upon dt is 2. Y is 3. Dy upon dt is required. So, with this help we can say the answer of dy upon dt is coming minus 8 by 3. So, rate of change in the decrease of the height of the wall in these conditions is minus 8 by 3 meter per second.